Hi there. Uh, we've not assembled here for a religious discourse, nor are we here for a star-studded rock concert. But we could still have some fun, right? Uh, I remember as a small child, we used to be a group of around 15, 20 friends who would loiter around and, do a host of useless things. And I was the youngest and the smallest looking of all of them. And occasionally I used to play some games with them, sense that I would tell them I'll show you black magic. Uh, and I would tell them, let's say at the end of a football game, I would say, okay, let's sit down together and let me tell you a few things. And it'll be true. I would tell them, look, there must be two amongst us born in the same month of the year. And I would tell them there must be two amongst us born in the same day of the week. And it'll all turn out to be true. Uh, and they would often wonder. They were relatively not that smart, much older and not really very smart, and they would often wonder, hey, where is it all coming from? They would scratch their heads and keep wondering where it all came from. And I would keep procrastinating, postponing an explanation to this. And I would create black magic, the so-called black magic of this kind, every once in a while. Uh, Now, this was almost when I was a kid, I would do this. Later on, when I became a formal student of mathematics, I realized that this was something that was formally taught as part of serious as well as recreational mathematics. Even though it would sound recreational to begin with, it had some very serious implication, and it would find a place in a host of very useful things. So what I'm going to share with you is some fun mathematics, recreational in appearance, but a wide variety of applications that it could have had. So let me tell you what I'm there to tell you today. See, there are M pigeons. M pigeons. Instead of pigeons, you could have taken dogs. Does not matter. But let's start with M pigeons. And say there are N pigeonholes. And the number of pigeons larger than the number of pigeonholes. M greater than N. Say these were the pigeons. P1, P2, PM. These were the pigeons. M pigeons. And let's say these were their pigeonholes. A1, A2, AN. These were the pigeonholes. And the number of pigeons more than the number of pigeonholes. And after all, what do you want to do with the pigeons? You want to place them in the pigeonholes. Now, if you want to place these pigeons in the pigeonholes, you have an option of placing one pigeon in a pigeonhole or more than one pigeon in a pigeonhole. Now, the rule is, when you start to delegate these pigeons to these pigeonholes, and if the number of pigeons are larger than the number of pigeonholes, would you not want to believe that there must be at least one pigeonhole, with more than one pigeon, isn't it? Because the number of pigeons are larger than the number of pigeonholes. Therefore, there must be at least one pigeonhole, ought to be one pigeonhole at least, with more than one pigeon. Because if there is no pigeonhole with more than one pigeon, then all the pigeons couldn't have been accommodated in the pigeonholes. Right? Popularly, this principle, which is essentially, a piece of very ordinary, mundane, down-to-earth logic, is referred to as the pigeonhole principle. Now, it might seem so odd to you to to go through this because it seems so obvious. It seems really, really obvious that if there are more pigeons and lesser number of pigeonholes, and you start to distribute these pigeons and pigeonholes, ought to have been at least one pigeonhole with more than one pigeon. Yes, prima facie, yes, it is very ordinary piece of logic, but it indeed has extraordinary applications. Part of recreation, like I said, and also part of very serious mathematics. But this one session, we would have a little bit of a diluted approach to pigeonhole principle. More serious stuff would follow once you get a hang of the pigeonhole principle properly. Now, look, I want to make a few statements and look at the validity of this. If you are more than 7 people watching me at this point of time, if you are more than 7 people watching me at this point of time, then let me guarantee you that there must be at least 2 amongst you. There must be at least 2 amongst you born on the same day of the week. There must be at least 2 amongst you born on the same day of the week. Let's say there are 20 of you who are watching me, and let me call them A1, A2, A20. 20 of you watching me right now. And the days of the week on which you could be born, the first day, Monday, let's say, and then Tuesday, and then Sunday. These are the 7 days of the week. 7 in numbers, right? And I start to assign you to the corresponding days on which you were born. I mean, if A1 was born on a Monday, I put A1 in this slot. If A2 was also born on a Monday, I put A2 in this slot. If A20 was born on a Sunday, I put A20 in the slot, right? So I start assigning the 20 people who are watching me right now, maybe more, to these days of the week. I treat these people as the pigeons and the days of the week as pigeonholes, right? Do you realize that the number of people, 20, that means the number of pigeons, are more than the days of the week, which is the pigeonholes? Do you then realize that there must be at least one of these slots containing more than one amongst you? Yes or no? There must be at least one of these slots containing more than one amongst you. For if that was not the case, how would you accommodate all 20? 2 distinct number of slots. There aren't that many slots available. Therefore, there must be at least one of these slots in which there are 2 or more people, which is essentially a direct consequence of pigeonhole principle, right? So then, if there is, let's say, slot 2 in which there are 2 or more people assigned, that means there must be at least 2 of you born on Tuesday. So there would be at least one of these days in which there are 2 or more people born, which was a simple consequence, implication of the pigeonhole principle. Again, 20 of you watching me, and I claim again that there must be at least 2 amongst you born on the same month of the year. Could be different years, but must necessarily be born. At least 2 of you must be born on the same month. Why? What are the months? The 12 months are January, February, March, December. These are the 12 months. How many of you are there? You're 20 of you, say. So do you realize that if I start assigning you to these slots, which are my pigeonholes, and you once again being the pigeons, then there must be at least 2 of you assigned to the same slot. There must be at least 2 of you assigned to the same slot. If there are at least 2 of you assigned to the same slot, that means you're born on the same month of the year. Same month of the year. So if there are more than 12 people, then there must be at least 2 born in the same month of the year. Now, let me go a little further and give you some more into pigeonhole principle. Say, for example, there is an equilateral triangle. ABC. That's an equilateral triangle. And let's say of each side equal to 2 units. Let's say each side of the triangle is 2 units. Now, what I do is, I have these 5 polka dots. These are 5 dots. And I pick these dots and start hurling them randomly within the triangle. I take this dot and I hurl it randomly in this triangle. I take this dot, I hurl it randomly in this triangle. I take this dot, I hurl randomly in this triangle. This dot, all the 5 dots. These are 5 dots. And I hurl these dots randomly inside the triangle. When I do that, I claim that there must be at least 2 of these points. I claim that there must be at least 2 dots. At least 2 dots whose distance does not exceed 1 unit. When I hurl these dots in the triangle, I claim that there must be at least 2 dots, no matter how I hurl them in the triangle, such that the distance between them is no greater than 1 unit. No greater than 1 unit. Now, how does one obtain this? You might be seriously thinking that it's a case of a very elaborate, complex mathematics of probability, mathematics of complexity, and so on and so forth. But to tell you very honestly, this is within the jurisdiction of any layperson. Someone who's not even had very great amount of training in mathematics can also comprehend why this is so. Like I said, pigeonhole principle is as simple as it was stated. In issues that involve pigeonhole principle, the point of consideration would be to obtain the pigeons and obtain the pigeonholes. Who you would want to call the pigeons and where the pigeonholes lie. What would be the pigeonholes? What would be the pigeons? That would be the matter of contention. That would be the choice that you would have to make based on your logical disposition. Now, what I do here is, in my attempt to define the pigeonholes, see, this is a little bit of an extraneous thought that would have to come to us with a little more exposure. Now what I do is, I break this bigger triangle into 4 identical triangles. How do I do that? If I join the midpoints of the sides of the triangle, if P, Q and R are the midpoints of the sides of the triangle, then do you realize that each of these triangles would be identical and would be equilateral? Each of the triangles would be identical and equilateral. And the side of each triangle would be 1 unit. The side of each of these triangles, the smaller triangles, the 4 smaller triangles would be 1 unit. Very clearly then, I now start taking these dots. I call these dots my pigeons. Now these beloved pigeons and these sedate, harmless, benign pigeonholes, these are my pigeonholes. So what if they are placed like this? They don't have to be placed end to end. This is how my pigeonholes are placed. These 4 small triangles are my pigeonholes because they would serve as the residence or the place where the pigeons would be accommodated. So these pigeons, I take this pigeon, chuck here. It will occupy one of these pigeonholes. I take this, it will occupy one of the pigeonholes. Now there are 5 pigeons. 5 pigeons in this case, and 1, 2, 3, 4. 4 pigeonholes. 5 pigeons and 4 pigeonholes. Do you then see that there must be at least one of the pigeonholes with more than 1 pigeon? That's pigeonhole principle, as simple as that. So which means, let's say, there must be at least one of the triangles containing at least two of the dots. There must be at least one of the triangles containing at least two of the dots. Yes or no? Right? And if that's the case, if there is at least one triangle containing two of the dots, call them P1 and P2, then the distance between these two dots found in the same triangle, the distance between these two dots found in the same triangle cannot exceed the side of the triangle, isn't it? So P1, P2 cannot exceed the length of the side of the triangle. The length of the side of the triangle is 1 unit, And that proves our assertion, right? So it's not about the principle, it's about the fact that you have to identify the pigeons, identify the pigeonholes. That discretion would be crucial and critical. How to define the pigeons, how to define the pigeonholes. Let me take you a couple of steps further. Let me illustrate a little more, because the principle is very simple. Exposure to the principle will be relevant, right? Let's understand. So this was a geometric application of the pigeonhole principle, right? Let's look at some more. Say, there are n people. Let's say these are n people. And from amongst them, they have friends. P1, for example, could be friends with P3 and Pn. P2 could be friends with P1 and P4, and so on and so forth. So they have mutual friends. It's not like they are all friends of everyone else. It's not like everyone here is a friend of everyone else. But then it's a group of people in which they have friends. Each person could have one or more friends. Let me assume that each person has at least one friend. There are n people in which each person, let's say, has at least one friend. Group of n people in which each person, let's say, has at least one friend. So, in general, P1, for example, could have had one friend, P2 could have had 3 friends, P3 could have had 4 friends, P5 could have had 2 friends, and so on and so forth. So they have friends in this group. Now, I make a subtle remark here. I repeat. There are these n people in which each one has at least one friend in the group. It could be more than one friend also. But it's not like everyone is necessarily a friend of everyone else, right? P1 could have a certain number of friends in the group, P2 could have had certain number of friends, P3 could have had certain number of friends, Pn could have had certain number of friends. Now, what I claim is that in this group, there exist at least 2 people. I claim that in this group, there exist at least 2 people having the same number of friends. There exists at least 2 people in the group having the same number of friends. This is my assertion, right? Let's look at it now. Of course, since it is within the jurisdiction of pigeonhole principle, we are pretty much directed mentally, intellectually towards how to handle this problem. But like I said, the most important aspect would be to understand what the pigeons are and where the pigeonholes lie. What would be our pigeons? What would be our pigeonholes? That's the aspect that one would have to discover in any given situation. Sometimes it could be blatant, upfront, ready-made, served on a platter. sometimes it could be a little camouflaged. In this case, it might be a little camouflaged to figure out the pigeons and the pigeonholes, right? Pigeons, of course, in this case, it seems obvious. The pigeons must be the people. P1, P2, Pn, these are my pigeons. But then, to really sort issues out, I would have to know where the pigeonholes are. What would I refer to as pigeonholes in this situation? Alright. So, the assertion, I repeat, just in case you've lost track, the assertion is that there must be at least 2 people in the group having the same number of friends. Not the same friends, but the same number of friends. That is what I want to tell you. Okay. Now, the number of friends is the issue. What I do is, what are the various possibilities? What are the various possibilities? These are n people. These are n people. Now, the number of friends any person could have had, right? The number of friends any person could have had is 1. Number of friends any person in this group could have had is 1, or 2, or 3, or 4, or n minus 1, isn't it? Because there are n people. A person wouldn't have n friends. I mean, person is always a friend of himself, but we will assume friends other than himself, his own self. So then the number of friends any person could have had would be 1, or 2 friends, or 3 friends, or 4 friends, or n minus 1 friends, right? Now, what then would be my pigeonholes? Let me create pigeonholes of the following kind. 1 pigeonhole, any person who has 1 friend. Any person who has 1 friend is put into this slot. 1 pigeonhole. Any person who has 1 friend is put into this slot. Any person with 2 friends is put into this slot. Any person with 3 friends is delegated or assigned to this slot. Any person with n minus 1 friend. Any person with n minus 1 friends is assigned this slot. Right? So these are my pigeonholes. These are my pigeonholes. A person with 1 friend is placed in this slot. A person with 2 friends is placed in this slot. Person with 3 friends is placed in this slot. Right? So how many are these slots? N minus 1 slots? And how many people? How many pigeons? N pigeons? Number of pigeons more than the number of pigeonholes. Do you realize that? N pigeons and number of pigeonholes n minus 1. Is it possible? Is it possible that every single pigeonhole has, rather let me rephrase it, is it possible that you have pigeons assigned to different slots? All pigeons, can they be assigned to different slots? No, it's not possible. Why? Because the number of pigeons are more than the number of pigeonholes, which means there must be at least 1 hole here with more than 1 pigeon. If there is, isn't it? If there is no hole with more than 1 pigeon, then the number of pigeonholes are not adequate enough to accommodate the pigeons, right? So there must be at least 1 hole here, at least 1 pigeonhole here with more than 1 pigeon. And if there is at least 1 hole here with more than 1 pigeon, for example, this is the hole with more than 1 pigeon, that means more than 1 person delegated to this, then there would be at least 2 people having 2 friends. If this is the hole with more than 1 person, then there would be at least 2 people with 3 friends, So that proves our assertion. Since there would be at least 1 hole with more than 1 pigeon, there would be at least 2 people with the same number of friends. That's a consequence of pigeonhole principle. How about it, right? Seems all right, isn't it? Let me give you another illustration. So far so good, right? No issues with it. Let me illustrate a little more. Say there are n plus 1 natural numbers. Say there are n plus 1 natural numbers. Random. Say there are n plus 1 natural numbers, pretty random. Could be located anywhere, right? Say these are the natural numbers: a1, a2, a3, an plus 1. These are the natural numbers. N plus 1 distinct natural numbers. N plus 1 distinct natural numbers anywhere. Not necessarily consecutive. Not necessarily consecutive. Now, I claim. My claim is. What's my claim? There must be at least 2 of these. Two amongst them. Such that their difference is divisible, by n. I claim there are these n plus 1 natural numbers. I claim them that from amongst them there must be at least 2, such that the difference between them is exactly divisible by n. Do you realize that? It seems so abstract, isn't it? I mean, how do we really connect, concatenate, link them all together, paint them on a common fabric? This seems, to begin with, a little more advanced case of a pigeonhole principle, Again, in most cases, it's a lot easier to discover the pigeons. The pigeons would be these natural numbers, n plus 1 natural numbers. It might seem so. And the pigeonholes is what we need to discover for this situation. We need to decide for ourselves what our pigeonholes would be like. So there are these n plus 1 arbitrary natural numbers. I claim that there must be at least 2 amongst them, such that the difference between them is perfectly divisible by n. Let's get a hang of this. Okay. One thing, when you divide a number by n, there is any number a and you divide it by n. What happens when you divide a number by a natural number n? What happens? There is a quotient q, isn't it? When you divide any number a by n, there is a quotient q plus a remainder r by n, isn't it? That's the division algorithm. R is the remainder of this division. R is the remainder of this division. When you divide any number by n, any natural number by a natural number n, then it leads to a quotient q, a remainder r, etc. I mean, 5 divided by 3, right? What does that give me? 1 as the quotient plus 2 remainder by 3. 3 is the divisor. That's what transpires, right? Now, let's understand this. So, division by n leads to a quotient and a remainder r. Now, when you divide by n, what are the permissible values of the remainder? The remainder r, when you divide by n, could be 0, right? If it's 0, that means a is perfectly divisible by n. The remainder could be 0 when you divide a number by n, right? That's when a is perfectly divisible by n. The remainder could be 1. The remainder could be 2. The remainder could be 3. And the remainder could be n minus 1, isn't it? These are the permissible values of the remainder. When you divide by n, the remainder could be 0, 1, 2, 3, up to n minus 1, right? Now, once I claim this, I hope you realize that when I divide by 3, when I divide by 3 a certain number n, then what are the remainders? The remainder could be 0, 1 or 2. These are the possible values of remainder. When you divide by 5, what would be the possible permissible remainders? 0, 1, 2, 3, 4. When you divide by n, what would be the permissible values of the remainder? 0, 1, 2, 3 up to n minus 1. These would be permissible values of the remainder. Now, what I do is, I create slots. This slot is about remainder 0. This slot is about remainder 1. This slot is about remainder 2. This slot is about remainder 3. And this slot is about remainder n minus 1. Dividing by n produces this set of remainders 0, 1, 2, 3 up to n minus 1. Up to n minus 1. Now, these are n plus 1 numbers. These are n plus 1 numbers, right? And the number of remainders are how many? How many possibilities of remainders? N possibilities, isn't it? This is one possibility, second possibility, third possibility, fourth possibility, n minus 1 possibilities. N minus 1, right? So which means, how many possibilities in all? N possibilities. Right? Remainder, this is one possibility, remainder 0. This is another possibility, remainder 1, second possibility. Third possibility, remainder 2. Fourth possibility, remainder 3. Nth possibility, remainder n minus 1. So these are n possibilities, right? So now these are numbers. A1 is divided by n. It could have remainder 0, 1, 2, 3, n. So it would belong to one of the slots when you divide A1 by n. When A2 is divided by n, the remainder of that division could be 0, 1, 2, 3. So A2 would be assigned one of these slots. A3 would be assigned one of these slots. An plus 1 would be assigned one of these slots. So which means, in general, I divide A1 by n, it will have a certain remainder. Based on the remainder obtained, A1 would be assigned a certain slot. For example, if A1 is divided by n and the remainder is 1, then A1 would be dumped into this slot. If A2 is divided by n and the remainder obtained is 3, then A2 would be dumped in this slot. If A3 is divided by n and the remainder obtained is 1, then A3 would be assigned this slot. If An plus 1 is divided by n and the remainder is 5, it would be assigned a slot with r equal to 5, right? So these numbers, these n plus 1 numbers are assigned these n slots based on the remainder produced out of dividing these numbers by n. Which means now there are n plus 1 numbers, n plus 1 pigeons, but only n pigeonholes. N plus 1 pigeons, but only n pigeonholes. What does it mean? If there are n plus 1 pigeons and n pigeonholes, there must be at least one pigeonhole with more than one pigeon. What does it mean? These are n plus 1 pigeons, n plus 1 pigeons and n pigeonholes. There must be at least one pigeonhole here with more than one pigeon. That means there exists a certain value of the remainder r. There exists a certain value of the remainder r, right? Which could be 0, 1, 2, 3 up to n minus 1, in which there are at least two pigeons. That means in which there would be a certain AK and there would be a certain AJ. Two of these AIs must belong to a slot with remainder r, at least two. That means there exist at least two numbers in this slot, which when two numbers in this collection, which when divided by n will produce the same remainder r, which means two numbers, say AK and AJ, when divided by n, there exist two numbers, at least two numbers, which when divided by n are producing the same remainder r, and therefore, which means AK when divided by n is producing a quotient Q1 plus a remainder r by n. AK when divided by n, for example, AK, a certain number belonging to this slot, when divided by n will produce a quotient plus a remainder by n. Another number AJ, which is a member of this collection, which when divided by n is producing a quotient Q2 plus a remainder r by n. Yes or no? There are at least two numbers which when divided by n will produce the same remainder R will produce the same remainder R. That's a consequence of pigeonhole principle. And now, having said this, let me carry out the following. Let me subtract this. Let me subtract these two. AK by N minus AJ by N. AK by N minus AJ by N is Q1 minus Q2. Q1 is a quotient. Q2 is another quotient. Q1 and Q2 are natural numbers, by the way. Q1 and Q2 are natural numbers. So Q1 minus Q2 would also be an integer. Q1 minus Q2 will be an integer because Q1 and Q2 are natural numbers. Which means AK minus AJ when you divide by N, AK minus AJ when you divide by N is producing an integer. But AK minus AJ divided by N, if it produces an integer, it implies that AK minus AJ must be perfectly divisible by N. And if AK minus AJ is perfectly divisible by N, we've been able to identify the fact that there exist two members of this collection of numbers such that their difference is perfectly divisible by N. That's another very, very useful, sweet looking illustration of the pigeonhole principle. This much for this session. I want you to ponder over it, think about it, evaluate more cases of this kind, and it'll be joy all the way. That's all for this moment. We'll see you with more advanced pigeonhole principle after some time. Thank you. Bye-bye.